Hey guys, so this time we're going to work on chapter 3, section 4, so measures of position and outliers. So we're going to learn about, well, just how we could interpret the data. All right, so determine and interpret z-scores. So z-scores are going to be really important for finding our, how far away we are from a value, or like last section we learned about the empirical rule, so we're going to look to see how far we could get away from a value, or how many standard deviations we are from a given value. So looking at population z-score, we're going to use our population parameters. So x minus the mean divided by the standard deviation. Over here again, it's x minus the mean divided by the standard deviation. So please note that here we have our population mean, population standard deviation. Over here we have our sample mean, sample standard deviation. Both of them are considered z-scores because what we're going to do is see how far away we are from the mean. So deviation from the mean divided by the standard deviation, that's going to tell us how many standard deviations we are away from the mean. All right, so next, determine whether the Boston Red Sox or the Los Angeles Dodgers had a relatively better run producing season. So here we have the Red Sox scored 876 runs and play in the American League, where the mean number of runs was 731.2. Standard deviation was 72.6. Dodgers scored 804 runs and play in the National League, where the mean number of runs was 710.8 and the standard deviation was 60.2 runs. So we're going to grab this information and take it to our notebook, because this section is going to be primarily out of our notebook. All right, so here I just took a snapshot, pasted it to a notebook, and now we're going to get started on this part. So here, what they told us, our z-score for population was x minus the mean divided by the standard deviation. And also z-scores could be found with the sample data. So we have x minus the mean divided by the standard deviation. Remember, mu is our mean for our population. X bar is our mean for our sample. Sigma is our standard deviation for the population. S is our sample standard deviation. So here what we're looking at are these scores here. And let's highlight the useful data that we're going to get here. Let's do a Dodger blue. Well, not really Dodger blue. Okay, to determine whether the Boston Red Sox or the Los Angeles Dodgers had a relatively better run producing season. Red Sox scored 876, and number of runs was mean of 731, standard deviation of 72.6. Dodgers scored 804 with a mean of 710.8 and a standard deviation of 60.2. So we're going to work with these individually. So let's start with the Boston Red Sox first. So now for the Boston Red Sox, what we're going to do is identify everything. So X in this case is going to be that 876. And they already told us the mean. The mean is equal to 731.2, standard deviation of 72.6. So let's calculate this z-score and see what we end up getting. So z is equal to x minus the mean divided by the standard deviation. X minus the mean is going to be 876 minus 731.2. And we're dividing this by 72.6. And we could grab our calculator and calculate this. So keep that there. And now we have our calculator. So our numerator is 786 minus 731.2. And that gives us 144.8. So we could write that down over here. 144.8. And we're dividing this by 72.6. So divide that number by 72.6. And that gives us a value 1.99449, so 45, 1.9945. Since it's relatively close to 2, we could just say that it's equal to 2. So that's for the Red Sox. Now let's look at the stats for the Dodgers. So for Dodgers, X in this case is 804. National League, mean number of runs. Mean is equal to 710.8 with the standard deviation of 60.2. And same thing here, we have our z-score is equal to x minus the mean divided by our standard deviation, which in this case, x is 804 minus 710.8, the standard deviation of 60.2. And now subtracting those two values in the numerator, we have 804 minus 710.8. And that's our numerator, so 93.2. And we're dividing that by 60.2. So that value divided by 60.2. And that gives us 1.54817, so 82. There we go. And now that gives us our z-score. So now looking at these, let's see. We have 876 for the Boston Red Sox, so that number is pretty high. 804 for the Los Angeles Dodgers. And here with the Red Sox, the numbers were relatively higher overall. With the Dodgers, a little bit lower than what the Red Sox had. And even with the dispersion too, the Red Sox had a higher dispersion rate. But what really matters to kind of see whether they were doing better or not, we have these two scores here. And because this one's larger, remember we said anything greater than 2 standard deviations from the mean is always going to be unusual. So let's kind of look at our empirical rule. So my best to draw pretty normal. So here we would have the mean. Remember, within 1 standard deviation, we have 68% of the data. Within 2 standard deviations, we have 95% of the data. And lastly, within 3 standard deviations, we have 99.7% of the data. So if we were to judge this right here, the Dodgers would be at 1.5. So this is 1.5 is about here-ish. And here it's well within the 95% of the data. So pretty impressive because we are over 1 standard deviation from the mean. But if you look at the Red Sox over here in pink, it's a lot higher. So it's a lot closer to 2. So it being closer to 2 is a lot further away than what we would like, or not what we would like it to be. It's a lot further away, meaning that it's going to be a lot larger than, it's a little bit more abnormal than what the Dodgers have, because the Dodgers are only 1.5 standard deviations from the mean. This one's really close to 2, so still catching within that 95% of the data, but getting really, really close to falling out of that 95%. I'd say they're within the 90, like, could even say 90%. Here, the Dodgers are within the middle 70% ballpark. But yeah, Ballpark as Dodgers. Get it? No. All right. I'm sorry. I'll come back to teaching. So there we go. That's all the standard deviation is. And I just brought this in here so we could kind of compare it to the empirical rule. But now let's get back to the PowerPoint and let's see what they say. So here, a lot of the data is missing. A lot of the slideshow is missing. And there should be a minus sign right there. And equals here. And just like we said earlier, this right here is a little bit different for, this is more normal than this is over here. This is getting close to unusual. So it being an unusual score and it being greater than the mean, it's an unusually large score for us to have that right there. All right, so the Red Sox had a run production of 1.99 standard deviations above the mean, while the Dodgers had a run production of 1.55 standard deviations above the mean. Therefore, the Red Sox had a relatively better year at scoring runs than the Dodgers. And now that we have that down, we're going to talk about interpreting percentiles. So the kth percentile denoted P sub k of a set of data is a value such that k% of the observations are less than or equal to that value. So just like we did when we were talking about our cumulative data, we're starting from the very beginning and adding on. So whenever we talk about the 10th percentile, so P sub 10, what we're looking at is the bottom 10% from the top 10%. So the top 10% is going to be this value over here. I'm sorry, the top 90% is going to be this value over here. When we're looking at P sub k, we're looking at just, when we're looking at P sub k, we're looking at just that bottom k%. Whenever we talk about P sub 90, looking at the 90th percentile, we're saying that 90% of the data falls below that value. The other top percent, the top 10% will fall on the opposite side. And let's clear this out. All right, yep, there we go. Just like the drawing says. All right, now looking at this, Jennifer just received the results of her SAT exam. Her SAT mathematics score of 600 is in the 74th percentile. So what does this mean? So I'm not exactly sure what the highest you could score on the SAT is, but what we're saying is this, the score of 600 is at the 74th percentile. That means we have like a score of 0 and a score of, I don't know, I'm just going to round, like give a ballpark answer over here and say 800. I'm not sure. Not exactly sure what that would be. This right here would be P sub 0 because we have 0% at 0 and P sub 100. So the 100th percentile is going to look at the entire part. So that means with the score of 600, there's 75% or 74% of people scored lower than her and 26% scored higher. So 74% lower and 26% higher. So her scoring in the 74th percentile means that there's 74% of the people that took the exam that scored lower than her, 26% that scored higher than her. So I personally would be pretty proud of that exam score. And the way they interpret this as being at the 74th percentile means that 74% of the SAT mathematics scores are less than or equal to 600, and 26% of the scores are greater. So 26% of the students who took the exam scored better than Jennifer. All right, now looking at this, quartiles are pretty similar to percentiles. With percentiles, we're breaking up the entire data set into 100 pieces. With quartiles, think of quarters. We're breaking it up into 4 pieces. So we have our first piece here, our second piece here, third piece right here, and fourth piece right here. So 4 separate pieces. And we're getting a little flashback from section 3.1 right here. So the median is going to make up one of those quartiles. So let's clear that out. So we have our broken up into 4 different percentiles. So the first quartile denoted Q1 divides the bottom 25% of the data from the top 25% of the data. Therefore, the first quartile is equivalent to 25th percentile. So we have that equivalent. So we have P sub 25, the 25th percentile, is equal to the first quartile, Q1. All right, and next we have the second quartile divides the bottom 50% from the top 50%. Second quartile is equivalent to the 50th percentile, also equivalent to the median. So that's another fun one. So we have the median, which we learned in section 1, is equal to the 50th percentile, because we're looking at 50% of the data below and above it. And the last one is going to be Q2. So all 3 of those are equivalent to each other, which I find kind of fascinating. And the third quartile divides the bottom 75% from the top 25%. So that one's the third quartile. That one's equivalent to the 75th percentile, or P sub 75. All right, and now finding the quartiles. So we're going to arrange the data set in ascending order. We're going to determine the median, M, or second quartile, Q2. And once we do that, so divide the data set into 2 halves, the observations below to the left of M, and the observations above or to the right of M. The first quartile, Q1, is the median of the bottom half, and Q3 is going to be the median of the top half. Again, kind of confusing, but once we actually look at the data set, it makes it a lot easier. So here's our data set, and we're going to grab these numbers just like we did back in section 1, so chapter 3, section 1. We're going to grab this data and we're going to spread it out and actually put it in order so that way we could work with the quartiles. But we're going to have to do this by hand, because for some reason Excel doesn't like looking at this data set and giving us the actual quartile. So let's take a snapshot of this and we'll take it to our notebook. Okay. Okay, so here we have the data set, and first things first, we're going to put this in order, so just like we did for the median. And let's go ahead and get started. So let's see, the smallest value is 180, and I see that right here. So let's start with that, 180. Then I see the next one, 189. Then the next one, 370. And next one, let's start from the top, 6,000, anything in the hundreds, 700, 618. And then we have that 734. I'm sorry, 735. Anything else in the hundreds? 802. And doesn't look like there's anything in the hundreds. Now let's look at 10,000s. So we have 10,0384 or 10,034. No, I'm sorry, thousands. So thousands is going to be 1185. Then 1414. Then 1657. Let's actually cross these out. $16.57, then $19.53, then 2,332, two, 3,336, 3,000, 3,461, 4,668, 5,006,751, 7,000, no, 8, no, 9, 9908. Then we just have those two left. So 10,000, then 20,000. So 10,034, 21,147. All right, so now that we have all of the data set here, we didn't have enough room to write it all in one line. So we kind of broke it up into these two parts. But if you notice, everything's going to be in line. So the smallest value is going to be 180. And the largest value is going to be that large one. So 21,147. So looking at those numbers from here, we could actually find our quartiles. So starting off with Q1, Q2, and Q3. So Q2 is going to be the easiest one to find. Remember, when we have a data set, it's either the middle number of the data set or the average of the middle numbers of the data set. So looking at this data set, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So 18 being an even number, we're going to get the middle two numbers of the data set, and that's going to be our median. So the average of the middle two numbers is going to be our data set, or our median for the data set. So our middle two numbers makes it really easy that we wrote it out like this, because we have the top half and the lower half, or the lower half above, the higher half, upper half below. So looking at these two, our first, or our median, or our quartile 2 is going to be the average of those two numbers. So we could say this is equal to 1,657 plus 1,953 divided by 2. So remember the average of the two middle numbers. And now from here, we look at those numbers, we add the two top numbers and divide that by 2. So we could do that with our calculator. And we have 1,657 plus 1,953. And that number ends up being 3,610. And we're dividing that number by 2. So divided by 2. Oh, I see what we did here. So we have that number, and then we're dividing that by 2. There we go. So that gives us 1,805. So now that's our median here. I don't think we'll need a calculator after this, but that's our median. So 1,805 is the middle number of our data set. And because we didn't have a middle number of the data set, it's the average of the two middle numbers. But now, more importantly, what we have here is we have two parts of the data set. We've divided it by the upper half of the data, or the lower half of the data set versus the upper half of the data set. And now once we have that, we could find our quartile 1. It's going to be the median of our upper half. Quartile 3 is going to be the median of our upper half, or lower half. and upper half. I always get those confused because it's on top, bottom. All right. So here our quartile 1 is going to be the median of the lower half, which is this one. So now looking at this, we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 9 data values in the upper half. Because it's an odd number, we're going to find the middle number of that upper half. So the way we found the middle number there, it's going to be n plus 1 divided by 2. So in this case, it's going to be 9 plus 1 divided by 2, or 10 divided by 2, which is equal to 5. So the fifth number in our upper half is going to be the median. So we look here, 1, 2, 3, 4, and 5. So that tells us that this value right here is our median. So equal to 735. And we do the same thing here for our lower half. So here in our our upper half. So the upper half, 1, 2, 3, 4, 5, 6, 7, 8, 9. So same thing here, there's 9 data values. So we would do 9 plus 1 divided by 2. This is going to give us the rank of our median of our upper half. So that's going to be 10 over 2, which is 5. So the fifth number, and the cool thing is we could count either forward or backwards. So we have 1, 2, 3, 4, 5. So it's that 4, 6, 6, 8. 4, 6, 6, 8. But it also works if we count backwards. So 1, 2, 3, 4, and 5. So it's always going to be the middle number there because it's the middle number of that set. So it doesn't matter if we count from the bottom up or from the top down. It's always going to be the middle number. So here, just to make it a little bit neater, because we have things all over the place, different colors, we have our first quartile equal to 735. Our second quartile, that should be a 1. Our second quartile equal to 1805. And our third quartile equal to 4668. And these make up our 3 quartiles of this data set. All right, let's go back to the slideshow, see if we forgot anything. So we have our data set, we put it in numerical order from the smallest data value over here to the largest data value on the other side. Largest data value over here. And step 2, so since there are 18 observations, the median is going to be the median is going to be the middle number, or the average of the 2 middle numbers. So this would be the median equal to quartile 2. There's a plus in the middle right here, making it equal to 1805. Awesome. And then from here, we looked at the upper half, or I'm sorry, the bottom half of the data set. So the smaller numbers to the middle value. And the median of the bottom half ends up being the 5th number of that round, and it ended up being 735. Cool. And now the median of the top half, so the bigger numbers, and it ended up being 4668. Looks good. Awesome. And now for the interpretation. So to interpret the quartiles as percentiles. So for example, 25% of the collision claims are less than or equal to the first quartile, so 735. 75% of the claims are greater than 735. And then we could interpret the median. So half, or 50% of the collision claims are less than or equal to $1,805, or the 50% of the claims are greater than $1,805 or $1,805. And that was with the second quartile. Now for the third quartile, 75% of the collision claims are less than or equal to $4,668, and what is it? 25% of the collision claims are greater than $4,608. All right, so now find the quartiles of the collision claims data in this table. So this one's a little bit different. So 1, 2, 3, 4, 5, 6, still 18. Oh, this is using StatCrunch, using a couple of other models. But now we have our interquartile range. So now that we know how to find our Q3 and Q1, our interquartile range is going to be the difference between those two. So interquartile range is a range of the middle 50%. So remember what we're doing with quartiles is we're breaking the data up into 4 different pieces. And if we look at the range of these numbers right here, so if we look at this range right here, it makes up 50% because we have our 25% here, 25% here, and 25% here. So we're looking at the middle 25% of the data, and that's all we're looking at there. All right, so there's that. So determine and interpret the interquartile range of the collision claims data from an earlier example, or from the earlier examples. So IQR, so we have the third quartile and the first quartile. So we had the difference between those two. And if you don't remember what they were, it was this data right here. So Q3 that we found earlier minus Q1 that we found earlier. So that's all we have right here. And that ends up being that 3,933. So $3,933 is what makes up the middle 50% of the data. So the range of those possible answers is $3,933. So IQR is the range of the middle 50%. And in this case, again, 3,933. All right, so the mean collision claims is 3,874.4, the median 1,800. The median is more representative of the center because the data are skewed right. So if you do look at the data set here, let's take a look at it over here. If you see these, we have 180, 189. So all of these are less than $1,000, and we barely start touching $1,000 in the last 3 values of the bottom half of our data set. Looking at the top half, then we have 1,000. The numbers are slowly but surely going up. And then the very last one is this random $20,000 one. So $20,000 is not a good representation of the rest of the data set over here. It's way larger, even 180. Actually, those are pretty average for like the bottom half of the data set, but this 20,000 is really not a good justification of what a normal person is going to pay for these claims here. All right, so here again, like they said, the median is a better center that we could use to identify like the average amount of money that people spend on the claims instead of the actual average, instead of the calculated mean. Let's see, standard deviation, 5,300, interquartile range, 3,900. So the values of the range and standard deviation are affected by the claim, the extreme claim of 21,000 or over 20,000. So when the distribution of the data is highly skewed or contains an extreme observation, it's best to use the interquartile range as a measure of dispersion because it is resistant. All right, so looking at this, if we have a symmetric shape to the distribution, measure of central tendency, mean would be better, measure of dispersion, standard deviation. Whenever we have data that's skewed left or right, we're going to use the median as our measure of central tendency, and we're going to use our interquartile range as our measure of dispersion. And now describing the dispersion. So the direction describes the dispersion, means to describe its shape. So either it's skewed left, skewed right, symmetric. Its center, median or mean or median, and its spread, the standard deviation or quartile range, interquartile range. All right, so now, so check a set for outliers. And so when performing any type of data analysis, we should check the extreme observations in the data set. Extreme observations are referred to as outliers, and outliers can occur by chance because of error in the measurement of the variable during the data entry, or from errors in sampling. So if something is way out of the norm, or maybe there was like a data entry error. So an outlier is what we're going to find next. All right, so step one, determine the first and third quartiles of the data. 2, compute the interquartile range. Then determine the fences. So a fence serves as a cutoff point for determining outliers. So again, let's pretend that this is our data set here. We would have our minimum value, Q1, 2, and 3, and our maximum value. A fence is going to tell us that like this value over here is okay. So we could do a little check mark. But from our highest data value, if the fence is over here and it doesn't meet the requirements of the fence right here, then this is going to be an outlier. And we don't want to consider outliers part of the data set because they really are far off to the norm. So we don't consider those when we look at a data set. So that's all fences is. So now the way we compute it for our lower fence, we have our data set here. We have Q1, 2, 3. We could say our quartile 1, quartile 2, quartile 3. So with these 3 quartiles, a lower fence is going to start with quartile 1. So right over here, as soon as there we go. So starting with quartile 1, it's going to be a value smaller. With the upper fence, it's going to be quartile 3 and a value bigger. So value smaller, that's why we use a minus sign right here. Upper fence is going to have a value larger, so we're going to add our interquartile range. And also we're going to multiply 1.5 to our interquartile range using left and right. So multiply 1.25 and well, let's see an example of that. So once we finish that, so if the data value is less than the lower fence or greater than the upper fence, it's considered an outlier. All right, so check the collision coverage claim and data table 16 for outliers. So this data set right here. So now we said our interquartile range was the difference between our, let's see. So interquartile range was the difference between Q3 and Q2. So again, interquartile range is Q3 minus Q1. And from here, we would just grab those numbers. So 4668 minus Q1 is 735. And we calculate that. Four, 668 minus 735. And that gave us 3933. So that's our interquartile range for this data set. And now let's look at all of the different values that we could get there. So the smallest value we have was 180, largest value was 20,000. And algebraically, let's look at it first. So we have our lower fence. And we have our upper fence. So remember for the lower fence, it was Q1, so the lower value Q1, and then we're going smaller, so minus 1.5 times our IQR. Our upper fence is a higher number, so Q3, and upper we're going more, so plus 1.5 times our IQR. And here Q1, 735 minus 1.5 times our IQR, 3933. Q3 was 4668 This time it's plus 1.5 times our IQR 3933. And now we're going to compute these two values. All right, so this first value, 735 minus 1.5 times 3933. And perfect, that gives us a negative 5164.5. And now let's check the upper. So the upper here is 4668. This time it's plus 1.5 times 3933. And that gives us 10,567.5. And now let's see if we have any outliers. So from here, we're going to look at all the numbers, anything less. So remember our lower fence, we have our data set. Our lower fence is here, upper fence is here. So for our lower fence, if we have anything smaller than our lower fence, it's going to be an outlier. Anything larger than our upper fence is going to be an outlier. So looking at our smallest, our lower fence, a negative number, all of the numbers in our data set are positive. So here we would have no outliers. So no outliers based on our lower fence. Now our upper fence, it cuts off at 10,567. And looking at these values, yeah, so this one's not going to be part of our data set. This one barely makes it into our data set because it's pretty large, but it's still smaller than this number. So the only outlier we have is at 21,000. So outlier, let's make it super obvious. So outlier is our 21,147. So outlier because it's larger than our upper fence. So it didn't make the cutoff for our upper fence. And that's it. So from here, IQR, our lower fence was a negative 5,000. Our upper fence was a positive 10,000 plus. And we have step 4. So there are no observations below the lower fence. So the lower fence was not the problem. The upper fence, we did have a problem. So there was one observation above the upper fence, and that was the 21,147. And that ended up being our outlier. And that's it for our data set. I'm sorry, that's it for section 5.4. Not 5.4. So that's it for this section. If you guys have any questions, go ahead and email me. Sorry, I think I cut off. But if you have any questions, go ahead and email me. But if not, have fun with your homework. Good luck.